hell are these funky things? Today is the day we talk about monoids. So first, some housekeeping. We're going to extend our library of type aliases. So we already defined one type alias in a previous video, fn, which was just a simple alias for callable. And now we're gonna add another really nice function that I like to call transformation. Okay, so what does the type transformation do? It takes some kind of type t and it's going to return a function from t into itself. Okay, so examples, right? So I've defined two functions here, add1 and sub1. And as you can see, these functions are functions from int to int. So in other words, I could also define this as add1 is of type transformation of int is lambda function of x to x plus 1. Another example. I've defined a function here that is going to be a decorator. So let's say that I want to print a message, for example, my message, every single time this function add1 is called. So I'm going to parameterize my decorator by being able to pass some message into it. So I can call effect of message. That will return a function that takes a function. Okay, so this function f is going to be like add1. That's what we're going to be passing to it. It's taking f and it's returning inner. It's going to get called with star args. So in the case of add1 of 1, where star args is going to be accepting 1. We're going to print the message and then we're going to return the function f that we passed to add1 with the arguments 1. So it's going to just return the function as is, right? It's going to have the normal behavior, but in the meantime, it's going to print the message. And as you can see, if I run my code, you can see that it perfectly does what I expected. It will run add1 of 1. In the course of that behavior, it managed to print my message, and then afterwards it will print the final result. And now the question is, how are we going to type this function? Because I wanted to illustrate the usage of my type, and then this function that it takes add1 will return just another function from t to u. So this as a transformation on functions from t to u. Then we're going to define a second type that I'm going to call composition. So what does the composition type do? It takes some type t and it is going to return a function from t times t into itself, right? So the same as before, I've modified my function sub a little bit. This time it's taking two arguments, one of type int and another one of type int, and it's simply subtracting the two. And I just wanted to show you that I can also replace this function. I got my sub and it's going to be a composition on integers, and it's going to be defined as lambda xy x minus y.
And liar, I thought you were going to talk about monoids.
You're already there. The monoid is just a set of elements paired with a composition. And you also need an identity element with the property that the composition of the identity element with any element from the set is equal to the composition of any element from the set with the identity element is equal to that very element.
And now I'm going to show you why it's useful.
Okay, so get ready to swallow this stuff, Bill. I've implemented this function reduce right here, and this is a nice one. You can pass some kind of composition to reduce, and that will basically apply the composition to all the elements in some kind of iterable or set in order. So let's unpack this. I got my function reduce, and it's going to be a function from some kind of iterable, and it's going to flatten it into some type by combining the composition iteratively over all of the different elements. So in a function that accepts an iterable, right? So we're just putting it there so that we can make it recursive, which is cool. And then we're gonna destructure our iterable into the head and the tail. And we're returning the composition applied to the head together with this whole reduction again applied next to the tail, right? But of course it's possible that we're at the end of our iteration and then there will not be a tail. So if we didn't include this clause here, then it would go on forever. So now we have completely superpowers. Instead of having to define a separate function that iterates over all the elements of some kind of set when we want to manipulate the values every single time, from now on all we need to do is define our composition, and then we're able to collapse our set and obtain the result that we want. Okay, hope that you appreciate monoids now. Next time we'll talk about end of functors.